All right, IBAASL2. We're getting deeper into this whole like calculus, derivative, gradient, slope machine type thing. Today we're going to get a little bit more into equations of tangent lines and how they relate to the curves. So first, I have just a regular, chunk of a function right here. There's a couple of vocab words I want to throw at you guys. One of them is we've already been over, but I'll do it again. That if you have a line that just barely touches right here on the curve, this is called a tangent line. Now, there's going to be another term thrown at you guys called a normal line. Normal is all about, well, it's like a tangent, but it's perpendicular. So a normal would go exactly through this point right here, but it would be 90 degrees. It would make a 90-degree angle with the tangent line. So this here is a 90-degree angle. So this is called the normal. Derivatives, I've been calling them slope machines. They're a machine that tells you the slope of the tangent line at the point on the curve. I think where some people are having a disconnect is anytime we found the derivative so far, they're like, oh, that is the slope. Like the slope is 2x or something like that. No, if the derivative is 2x, that's just a machine that can tell you the slope of a tangent at any point on the curve, but you have to feed an input into it. You have to replace the x with something to figure out what the slope of a tangent is at a certain point on the curve. First example, find the gradient function. Remember, this is just another word for slope, and so we're going to find the slope function, which is just the derivative of this guy right here. Before we can find the derivative, and then the rest of the directions are find the gradient of the tangent to f of x where x is equal to 4. The first thing is this is not quite in the form where we can take a derivative because of the square root of x in the denominator. So we have to do a rewrite. The x squared is chill. The negative 4 can hang out there, but then the square root of x is x to the 1/2, and when you kick it back upstairs, it becomes a negative, x to the negative 1/2. Now you can take the derivative of both of these chunks. So do the power rule on this and do the power rule on this. So f prime of x is equal to 2x. Then the negative 1/2 comes out in front, so the negative make a positive. 1/2 times 4 is 2, and then it'll be x to the, negative half minus 1 is negative 3/2. Now, we agreed last class that we're not going to leave negative exponents in the, in final answers. So the 2x is chill, but then we need to move that x to the 3f's to the denominator. So this is 2 over x to the 3f's. Now, they ask us to find the derivative, find the gradient of the tangent to f of x where x is equal to 4. For this piece, we're going to plug that in to the derivative we found. So we're going to find f prime of 4, which is replacing all the x's with 4. So 2 times 4 plus 2 over 4 to the 3/2. Now, 2 times 4 is 8, but then that 4 to the 3/2, we almost have to do like a little sidebar to figure out what that is. You could just punch it up straight into your calculator, but I'll show you guys a little trick to be able to figure out what that is. So, let me zoom in right here. I rewrote the 4 as 2 squared. Why did I do this? Well, because I saw that there's going to be like a 2 in the denominator of the power. So if I rewrite this as 2 squared, when you have power of a power, you multiply their powers. So this becomes 8 plus 2 over 2 to the 2 times 3 halves. Now, 2 times 3 halves is just 3. So this whole thing is 8 plus 2 over 2 to the third. Oh man, we're gonna maybe run out of room here. 2 to the third power is 8. 2 times 2 times 2. So this becomes 2 over 8, which equals 8 plus 1/4 when you reduce that fraction. But then you need a common denominator between those two. So the common denominator, we have to change that into 32 over 4 plus 1 over 4. So this equals 33 over 4. Now, if you're looking at that and you're like, what just happened? What does that even mean? We found the derivative right here. Then we fed a 4 into the derivative. Crunch, crunch, crunch. We got this. That means that the slope of the tangent line to the original function at x equals 4 is 33/4. Next problem. Find the coordinates of the points on that whole thing where the gradient is 4. So now we're not putting an x value in. They're telling us what the slope is. Remember, the slope is the gradient. So they're saying that the derivative is equal to 4. First step, take the derivative. They're all set up nicely to do power rule. Bring those powers out in front. 3 times a third is just 1, so you get x, drop it down 1 squared. Then when you bring a 2 out in front with the 1/2, that also cancels out nicely, and you get minus x to the 1 power. Then remember the derivative of negative 8x is just the coefficient, so that's negative 8. And then there is the derivative of 7 is just 0. So there's your derivative. Now we want to know where that is equal to 4, where the slopes are 4. So we're actually going to replace this whole side with 4. Now we got a good old-fashioned quadratic on our hands. So subtract 4 from both sides, get it equal to 0. Now, two numbers that multiply to negative 12 and add to negative 1 are negative 4 and positive 3. Set those both equal to 0. You may remember the zero product property. Two things being multiplied to get 0, then one of them has to be 0, or both of them. There's the two spots. That's where on the curve the tangents would have a slope of 4. Just a reminder from past courses, if a tangent line has gradient m, so slope m, the perpendicular slope of the normal is going to be negative 1 over m. So turn it upside down, make it the opposite sign. The function, this is given, find the derivative at x equals 1. So first step, pop that derivative. It's just 6x. Remember that this part is a derivative of 0. Now we want to know what it is at 1. So we find f prime of 1, which is 6 times 1. So this is 6. Now we want to find the equation of the tangent at x equals 1. Well, from this part, we already know at x equals 1, if you put in a 1 into the derivative, you get 6. That 6 is a slope. Remember, x's go into derivatives, slopes come out of it because they're slope machines. So if you think of your y equals mx plus b for your tangent line, we already know the slope is 6 at that point. What we don't know is the y-intercept. So here's what we're going to do. I need to erase something. We're going to take the original function and put the x value into it to figure out what point the tangent is touching. Remember, tangents only touch the curve at one single point. That single point is where x equals 1, but I don't know what y value is associated with it. So we're going to plug x equals 1 into the original function. So that's f of 1 is equal to 3 times 1 squared minus 2, which is 1 as well. So that means, 1 comma 1 is on curve and on the tangent. I did not leave enough room. Now, if you take the y equals mx plus b, so y equals 6x plus b, and replace x with 1 and y with 1, we can solve for b. So 1 is equal to 6 times 1 plus b. So b is equal to negative 5. So the equation of the tangent is y equals 6x minus 5. Now we're going to find the equation of the normal at x equals 1. Well, the tangent slope is 6, which means that the normal slope is going to be that upside down and negative. So negative 1 over 6. So we know that the normal is going to be negative 1, 6x plus b. It's just y equals mx plus b with the slope replaced. And the normal, is also going to touch that same point that the tangent touches. If you look back up here, notice that the normal line and the tangent line both touch at the point that's on the curve. So the curve, the tangent, the normal, they all touch at that single point. We already found out that that point in this example is 1, 1. So really, we just have to plug a 1 in for the y and x. So plug the 1, 1 into the y equals mx plus b. Then here, negative 1, 6, you move it to the other side. So you get positive 1, 6. Then you need a common denominator. So 6, 6 plus 1, 6 is 7, 6. That's your y-intercept. Here's your final answer. Find the equations of any horizontal tangents to the curve this. So horizontal tangents, if you kind of look at this diagram, you can think about these tangents as like a surfboard that's like riding this wave here. And then like, as you go up this hill, the slope gets less and less until you get right up here to the top of the hill and you get a completely horizontal tangent. So a reminder, horizontal tangents, or horizontal slopes, I guess I should say, have a value of 0. Remember that a completely horizontal slope is 0 and a completely vertical slope is undefined. I always remember that because when it's horizontal, you can still walk on it, but if it was vertical, you couldn't walk on it. So vertical is undefined, horizontal is defined, it's 0. So slopes of those tangents, let's take the derivative. Find the slope machine. Straight up power rule. There it is. Now, we want to know when those slopes are equal to 0, aka a horizontal tangent. So set it equal to 0. Now it's a quadratic, And some people might look at that and go, oh man, do I have to multiply 6 and negative 12 and then find all the numbers that multiply to that and add to blah, blah, blah. But notice that all these numbers are divisible by 6. So you can actually divide both sides by 6. And 0 divided by 6 is just 0. There, much better. Nicely factorable. Two numbers that multiply to negative 2, but add to 1 are negative 1 and positive 2. Set them both equal to 0, and you get negative 2 and 1. Okay, you guys, that's all I have for you today. Good luck. Happy studying.